Hey everybody, it's Ripley back again. Going to give you a couple more convergence tests today, and these really are the keys to the kingdom. They're not the end-all be-all. They don't work in every situation, but they're really good convergence tests, and they're going to help us do some pretty powerful things mathematically down the road. The name of the first convergence test is the alternating series test. So alternating series test. And the alternating series test is super powerful, and it leads us to something called absolute convergence, which we'll talk about here in just a sec. You can refer to this as AST. Okay? Now let's define an alternating series first. So I've got an alternating. An alternating series is real simple. It's simply a series, so it's standard issue series that we've seen before. The only difference is, let's start it at 1, even though we know we can start wherever the heck we want. All right, and I'm going to use a b sub n instead of an a sub n here. And the textbook does this, and most other textbooks do this as well. It's just to denote, it's still just, this b sub n is just a sequence, right? It's just a bunch of terms that are ordered, right? But we're giving this thing some special love. All right, and what we've got here is we're saying this is a special type of series, and it's special for a reason. All right, what it does is it switches signs, right? Can you see that? So think about this. This thing is going to equal, if I let n equal 1, I'm going to have negative b sub 1 plus b sub 2 minus b sub 3, etc., etc. Right? But if you think about it, I could just as easily write this as the sum as n goes from 7 to infinity of negative 1 to the n plus 1 b sub n, right? Does that make sense? And well, let's instead of doing it at 7, let's do it at 1. I don't want to complicate things too much, but you can start them wherever you want. So I guess I'm being redundant with this. Now, what would this look like? Look at b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus dot 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 plus, and then we would say negative 1 to the n plus 1 b sub n plus dot dot dot. So really all that we're saying is that the terms change sign every other term. You gotta be real careful with that, because students will look at that and they'll have a series that changes signs like a sine. How about this? The sum as n goes from 1 to infinity of sine of n, right? Now, if you think about this, this would be sine of 1 plus the sine of 2, right? Plus the sine of 3 plus the sine of 4. Now this guy changes signs. I know that the sine of 1 is greater than 0, right? I know that the sine of 2 is greater than 0, but the sine of 3 is less than 0. Sine of 4 is greater than 0. So we have an alternating situation here, but it doesn't happen every other term. So if you don't trust yourself, if you're not sure if it's an alternating series, because they can look really crazy, in other words, if they don't have this negative 1 to the n plus 1, n plus 17, n minus 3, whatever, then chances are it's not an alternating series, even though they will change signs. Okay? So just be careful with that. Now, the alternating series test is actually very simple. There's nothing to it. It simply says, suppose I have the series as n goes from 1 to infinity. I'll go negative 1 to the n plus 1 b sub n, which we know is b sub 1 minus b sub 2. Did I do that? Let's see. n plus 1. Yeah, b sub 1 minus b sub 2, b sub 3, etc., etc. All right. All right. So if b sub n plus 1 is less than or equal to b sub n, less than or equal to b sub n, and so let's number these, and big underline 2 the limit as n goes to infinity of b sub n equals 0. Both of these assumptions absolutely have to be satisfied. If they're not, we're screwed. Okay? Then the sum as n goes from 1 to infinity of negative 1 the n plus 1 b sub n converges. Period. So look at how powerful that is. There's nothing to it. There's really nothing to it. What do we have to show? Let's go easy. First things first. We have to show that if b sub n plus 1 is less than or equal to b sub n, what is that? Think in calculus terms. What does that say? It means that the series is decreasing. the sequence b sub n is decreasing, right? And we can use all of our powers, all of our abilities, all of our skill sets as calculus people to determine decreasing, i.e., wink, wink, nudge, nudge, derivatives, if we absolutely have to, and we very rarely absolutely have to. And then all I have to do is show that it goes to 0. The limit as n goes to infinity goes to 0. That's it, and you're done, okay? Now, so for example, let's take the sum as n goes from 1 to infinity, nice and simple, of negative 1 times 1 over n. Oops, negative 1 to the n times 1 over n. All right, so if push meets shove, label a couple terms, right? Negative 1 plus a half minus a third plus a fourth. Now, your spidey sense may be tingling, but think about it. Is it an alternating series? Yes. Now, again, you may be saying, but Ripley, it's a harmonic. We know harmonics diverge. Whoa, 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 go easy here for just a sec. Let's think about what's really happening here, okay? I mean, if I think about this, if I want to graph this, I start at negative 1, oops, when n equals 1, and then I come down to a half, and then I come down here to a third, and then down to a fourth, and I'm getting ever closer and closer to 0, aren't I? And I'm adding those things up. I'm going to give you a real interesting graphical display here in just a sec. It's pretty cool to look at. So all that we're going to do is we're going to go by the alternating series test. By the alternating series test. 1. Since 1 over n plus 1 is always less than or equal to 1 over n for every n, and 2, the limit as n goes to infinity of 1 over n equals 0, we know the sum as n goes from 1 to infinity, negative 1 to the n, times 1 over n, converges. So the series 1 over n, which is harmonic, we've already proven, diverges, but the alternating series converges because we're subtracting out values. Now again, we don't know what it converges to, and I'm going to show you a way to figure that out, which is pretty cool. Excuse me. My throat is parched. You guys got me sick. Dang it. But we do know that it converges. And we'll play with that. We'll play with that remainder of that error term here in just a sec. All right? Easy enough, right? Nothing to it. So if I've got something like this, if I've got the sum as n goes from 1 to infinity, and I'm looking at this thing, and I'm like, okay, I got negative 1 to the n, and I've got, I don't know, the e to the negative x times x squared, right? All right, so what's the first thing that you might want to do with this thing? That's intimidating looking when you first look at it, but as soon as you see that little guy right there, as soon as you see that, you might think to yourself, well, I think that one's, now this one could be interesting. All right, so here's what we're going to do. First things first, it's an alternating series. I'm going to rewrite this because it helps my brain figure stuff out. When I see this as x squared over e to the x times negative 1 to the n, I'm like, okay, now I'm starting to understand this a little bit. So this is a considerably more tricky problem to play with. Okay, so I want to walk you through this entirely. All right, number 1. All right, so we're going to prove that the limit as n goes to infinity, I'm going to need some more room on this, God bless it. The limit as n goes to infinity of x squared, remember this is the b sub n part, that's just the sequence part, that's the thing that provides us with the ordered terms, and this is the negative 1 to the who cares part, right? Excuse me. So I have to prove that x squared over e to the x equals 0, all right? Well, that's easily done. I can do it by L'Hopital's. All right, if I do by L'Hopital's, I know that this equals the limit as n goes to infinity of 2x over e to the x. Why am I using L'Hopital's? Because this is infinity. Oops, this is infinity over infinity, right? No, still infinity over infinity. So by L'Hopital's, I have the limit as x approaches. Whoops, as n approaches infinity. As n approaches infinity of 2 over e to the x, sweet, equals 0. See how I'm using all of my powers, all of my skills to prove that this thing equals 0, that the limit is. I'm like, oh, I got to prove something equals 0. Well, let's use L'Hopital's if it's not immediately recognizable as something that goes to 0. All right, now the second part's a little trickier. Watch how this guy works. So let me rewrite my thing here. So n equals 1 to infinity, negative 1. I think I said negative 1 at the end, right? Not n plus 1. Doesn't really matter, though, in terms of proving whether or not it converges. Part 2. How do I show that b sub n plus 1 is less than or equal to b sub n? Easy. Watch. If f of x, let's go, if f of x is, well, I don't know where that came from, equals x squared over e to the x. Now, do you see that if I can show that if this function decreases for some values between n and infinity until infinity, then we're golden. Even if this thing were to increase from, say, n equals 1 to 15,000, and then it decreased from 15,000 to infinity, I'm good because I'm adding a finite number of terms between 1 and 15,000, and then an infinite number of terms from 15,000 back to 1, or back, 15,000 back to infinity. Remember, you can always remove a finite number of terms as long as they're defined. So, oh wow, that's hard to read. This implies that f prime of x equals low to high, so 2x e to the x minus high to low, which is x squared e to the x, all over e to the x squared. I'm going to set this guy equal to 0, so that implies that if I pull out an e to the x times x, then I get what? 2 minus x. Do you agree with that? Let's see, let's make sure I didn't screw something up. I think I did. Not. All right, so here we go. We're going to have critical points at x equals 0 and 2. All right, this is a great problem. God, I write a good problem from time to time. Now, we don't really worry about the 0, do we? But we do have to worry about when n equals 1. So here's 2. And then, of course, don't forget your f prime sitting over here. I'm not going to worry about anything to the left of 0 because n equals 1, right? So let's pick 1. Let's plug it in. Well, 2 minus 1 is positive. E to the 1 is positive. 1 is positive. So this thing increases from 0 to 2. And then 2 to infinity, right? I didn't have any other critical values. So let's say, I don't know, 15. Well, this term's going to be positive. This term's going to be negative. So I am decreasing. All right? Now, the way in which you write this is, you ready? I'm so glad I wrote this problem. This is a good problem. If I write this guy as the sum as n goes from 1 to infinity of negative 1 to the n times x squared e to the x. Now, here's the problem. This is supposed to decrease for all n, and at n equals 1, theoretically, we're not decreasing. All right, so here's what I'm going to do. I'm going to write this as, now what? Let's see if you can figure out what I'm doing here. I'm going to do negative 1 to the 1, 1, wait, why did I use x squared? This is where I put those little pop-up bubbles in and like ding dong, put n's, not x's. And did I do that throughout? If I did that throughout, I'm going to be so mad at myself. I'll bet you I did. It just feels like I did. That's all right. Let me go back and look. You guys are going to yell at me. I know it. You're always yelling at me. N squared over e to the n. I know I did, didn't I?